Good afternoon, ladies and gentlemen. Well, I've got two mics, so that's probably going to be confusing. I'm here on behalf of the Netherlands Defense Materiel Organization. I'll be telling you a little bit about how we in the MOD, Ministry of Defense, and particularly the Navy, as I'm Navy, how we use oceanographic data in our military application, and particularly now in sonar. How we use this to predict how well our sonars are going to work, both when we do mission planning and when we do an operation. Because oceanographic changes are a huge impact to how well a sonar performs. It can make the world of difference whether you see only half a mile or 20 miles. That's the big difference you have with just a few changes. So knowing that in advance gives huge importance to how we plan our missions. I'm here really not the expert. Tilly Druzhina should have been given this presentation, but she was detained, so she didn't come. Tilly was really more involved in the R&D, whereas I'm more involved in the actual applications and development of products. Good thing is, I use the models when I'm using the systems, so I've got quite a bit of operational experience with these systems. Outline of my presentation, a little bit about who we are, who's the demo. Then I'll go into sort of performance modeling, how it works, the problems we have, and obviously then I'll move into how we use and how we would like to use CMEMS products. So, DMO. In the Netherlands, we have one organization which is responsible for all equipment for the entire defense, so Army, Navy, Air Force, you name it. And I'm in the underwater technology department, so just the one tiny branch of it, but relevant for this particular session, actually. We do a whole lot. It's not just the systems, also the R&Ds, mainly with us, and then for this we work mainly with TNO. So Mark Breyer, he's giving a talk later this afternoon. Yes, we DMO task the development of sonar, sonar prediction models, but in this case, TNO does most of the actual R&D and the development of the systems. So why do we use all these various products in sonar modeling? I've already touched this briefly, but we have quite a few applications. We do mine hunting, we do submarine hunting. Obviously, we have submarines and they're in the water all the time. And if you compare it, you have the air. Air is, well, I'm an underwater guy, so I think air is easy. You have no boundaries. If you send a radar into the air, there's not really any reflection, easy. Go in the water, you have all these bounds, you have an unpredictable bottom, you have an unpredictable surface layer, you have unpredictable sound velocity profiles affected by temperature and salinity. So all that makes it very complicated, and it very much impacts how far away you can see a mine, how far away you can see a submarine, and how well a submarine can detect anything on the surface. So this is really why we use the models to have an estimate. We use these models at various stages. Obviously, you do a lot of planning in advance, and the better your model is, the better it will actually match how well the sonar will work in the field. Obviously, when you go into the field, like I say in the military, any plan fails as soon as you enemy contact, and that's basically the same with sonars. Yeah, you can do a whole lot of modeling, and you usually need to, but then you go into the field and you're there, and you need to actually measure a lot of stuff, because that will tell you how well it will really work. So, various stages in the advance, in tactics, in the planning, and then how we are going to be there. So, in a few steps, what do we put into a sonar model to actually predict what we're going to see? So we've got a sonar, various bunch of sonars, active, passive, you name it, but let's take an active sonar. We make sound. It goes into the ocean, it bounces against a whole lot of objects, and some of it get back. You've got the environment, like I mentioned, you have the bottom, you've got a surface, you've got all the oceanographic aspects to it, and you've got a target, a submarine, a torpedo, you name it. You put all of that into a model, and then you start doing a whole lot of calculations on how sound propagates, how it gets back, what is the ambient noise in the water, and it gives you sort of a probability of how well you will detect a certain contact at a certain range. Obviously, the reality is always different, but you need to do something. Let's see. Sonar performance model. So we have a few steps here. We've got refraction. So a few examples here. You got it bouncing up and down to the surface, to the bottom. You get a whole block of pictures. You get the bottom where it pleats. If it's a nice flat bottom, easy, but it never is. So it refracts quite different from how you would like it to go. That affects how the sound goes to the water and what you will get back. You have the surface, which the roughness will affect strongly how the sound goes to the water. And finally, then you have also the backscattering again, so bottom roughness. Example here. Suppose the world was ideal, the ocean was just one infinite medium, no bottom, no surface. The sound speed profile would just be constant over depth. Then if you put sound in the water, you get, well, basically it dilutes with distance. You get something back and it's very predictable. But that is not the case. So we get to the bottom and you send something from the left side and it starts bouncing against the bottom, against the surface. And you get something back and it becomes quite difficult to expect. So luckily here you've got quite a bit of signal to noise ratio, so you might be able to detect the contact. Here you certainly won't. That's really relevant to know. The submarine, I'm a submarine hunter, will try to put a submarine here because he knows you won't detect him, and we try to be in a position to be able to detect him. But knowing that is obviously important, so that's why oceanographic models and data becomes important for tactics. It's obviously highly unpredictable. The plot I just showed you shows that. And obviously it's not just unpredictable in one point, but also more importantly so with time. You're in a, basically when you are on an operation, what we do now is obviously we measure a sound speed profile, but that's at one point at one time, and then we hope that will be true for the area we are in for the next couple of hours. Usually not quite the case, but logistically you can't measure it all the time. So you have to do something, and going to use models might improve it. So we've touched on validity. Now there's variability also. Again, over space. We assume that the sound speed we measure is valid over the entire area, but you have got freshwater lenses, you have got internal waves, everything changes. So knowing that, again, important. I just mentioned internal waves. They're not only important for prediction of your sonar, they're actually important for submarines. Submarines underwater, they trim to ballast to a certain neutral buoyancy, and then you move around, and all of a sudden you've got an internal wave, different temperature, different density. So your submarine is affected and starts sinking. Not dramatic, but really relevant to know and to have a feeling about where that might happen. So a few examples here. Let's see what my colleague put up here. So you've got the bathymetry. So you've got a gradient, a slope against which sound will bounce. You've got a vertical certification, which means the sound speed profile is affected here. You've got a strong tide, which will affect it. And then what you end up with, well, the internal wave. You got all these other stuff. This is over time. So you measure the sound speed profile at time 0, and you're gonna hope that it's gonna be like that for the next 2 hours. But evidently, it's not going to be like that. And while you're expecting ranges of, like, for instance, 5 miles, when this happens, ranges go down to 1 or 0 miles, and there goes your plan. So now we go to combining data sets, and there is where CMEMS becomes important for us. We've got the sea slope data. We've got tidal strength direction. And we've got water column certification. And if you go and combine that, you've got the internal wave risk map. And we're then basically using the CMEMS data to get to this final map. You get the variability index here. The CMEMS, as I understand it, already has a 3D model for the Mediterranean. So the bottom figure you see on the bottom left, we're not in the Mediterranean, we are a bit further up north. And now we're interested in also getting the same kind of data for our area. So we can go and do the same, because these hourly updates with the 3D model, they can become quite important for us. In summary, for sonar performance modeling, we need some velocity data, which means salinity, temperature, pressure, but that's sort of predictable with that. If we go to a 3D model with an hourly update, that can help us a lot, because then you can start thinking about using an average for an area rather than a single point at a single time. If we use data which gives us better estimates of the roughness of the sea surface for an area, so the sea state, we would use a model rather than looking from the bridge and seeing, well, sea state 4, wave height about 2 meters. That's at that point, at that time, again, using that for a model for a certain amount of time gives you an offset, a bias. Seafloor, important for us, slightly more difficult to get with a satellite. And all these gives us estimates of internal waves and where sonar performance is going to be affected. Data existing, useful for us. So I showed the plot earlier, the data for the Mediterranean. Excellent data, we want more of that. Personally, we would like to see the same, more to the north, North Sea, Atlantic. Actually, we would also like to see the Caribbean data, as there's a few islands where Europe still has quite a bit of interest. So we as a fleet, the Royal Netherlands Navy, we have got 1 or 2 ships there all the time. We're hunting for drugs runners, and they start using submarines. So for us, it's important to also have data there to use sonar. We'd like to see more significant wave height data and directions, so we get to take that into account. And it's obviously not only sonar, we have got a whole lot more where we use it for military planning. And obviously then we've got bathymetric information because the bottom is very, very important. So that's what we would like to get from Siemens. I certainly hope you guys can help us. Are there any questions? Well, let's start with you.
Susanne Kamp from the